Good morning or good afternoon, and welcome back to computational mechanics. So, as promised today, I will release this theoretical video that is about the automation of the building of the global stiffness matrix. So, of the assembling the global stiffness matrix for our finite element problem. So, what does this mean? Well, you remember from our previous classes that we started working with finite elements by solving by hand the problem that you see up here. So we did this in two steps. The first time we just solved for the nodal displacements 1 and 2 in the global the global degree of freedoms 1 and 2. These were the loads. We did the load transfer to the nodes, and then we solved the system. And we obtained these two values. So U1 and U2 were equal to 8P over E. And we solved this by hand. We also solved this using the penalty method. Then we also solved the problem again, but this time introducing the reaction here by removing one of the constraints at this point. And again, we solved it both by hand and using the penalty method. In doing so, we obtain the reaction as minus 2p. Okay. Now, the question is, can we find a way to automatically set up the global stiffness matrix so that then we can invert it and then obtain our nodal displacements? Well, yes, and this is the content of this lecture. So first of all, what we need to do is, yes, identify and number our elements and then number our nodes, okay? Now, once you do that, you get your connectivity and coordinates of the node, okay? And when we want to solve the problem automatically, okay, the computer will not know whether there is a constraint or not in a node. So the first thing you can do is, well, let's highlight all the possible global degree of freedoms. So U1, U2, U3, U4, U5, U6, U7, and U8. So this is in general, we're not looking at the constraints, okay? These are all the possible nodal displacement if we had our structure was flying, okay? And we're not even looking at the loads for now. Then, well, we include the loads by using the, transferring distributed loads onto the node as we've seen already. And then we can also highlight all the reactions, okay? In general, if you didn't know the constraints of this structure, but you just knew it was formed by two elements with four nodes, you could then highlight all these reactions. Then if one is there or not, we can deal with it later. But to build a stiffness matrix, in fact, nodal loads and reactions will not enter in the problem. So we're used to build our connectivity table. And in the case where we highlight all the nodal displacement, we see that for finite element 1 and for finite element 2, we fill the table, okay? In fact, each element will have 6 local degree of freedoms, okay, of the element, but then it will have 6 of the global one because we're highlighting all of them. So it's always full, okay? For example, element 1, well, in this case, the numbering is exactly the same from global to local. So U1 will correspond to 1, direction 1 at the element scale, etc. Where for finite element 2, U1, okay, so actually in U7 is going to be the local U1. U8, okay, is going to be number 2, etc. So we can do this. Now, if you remember, once we have this, it's easy to set up the stiffness matrix. In fact, we're used to write our global degree of freedom vector, okay, and in this case will be U1, U2, until U8, and then we have a K global, that in this case, what's the dimension? Well, it's this size times this size. So in this case, it's an 8 by 8. So what is the dimension of the system as a function of the number of nodes? You immediately realize that for each node, we have 2 degrees of freedom in X and in Y. So how many degrees of freedom do we have for 4 nodes? 2 times 4, 8. So in fact, we see each node has 2, and therefore we can immediately write that the global stiffness matrix will be a 2 number of nodes times 2 number of nodes. So it's going to be an 8 by 8 matrix in this case, whereas the nodal unknowns, so the nodal displacements in the global system is going to be 2 times the number of nodes times 1 because it's a column vector. Okay, and then the equivalent nodal loads and reactions, we put them there, but we're not going to look at this at the moment. So we can then say that the global stiffness matrix is a 2n number of nodes by 2 number of nodes. The U is a 2n times 1 is equal to 2n by 1 vector. Okay, so let's now consider the following. We have our generic finite element mesh, and we have element I. So given element EI connected by nodes N1, N2, N3 of element EI, how do I calculate the 9 terms of the Kij of the element? Okay, and where will each of these 9 terms be positioned in the global matrix K? Well, we learned this today, and I hope this will be clear. And then I will also show you how we do this in MATLAB, and you can find the MATLAB script I show just under here where you're watching the video. So yes, can we assemble the matrix automatically having the core and con vectors, where coordinate is, well, the nodal the x and y position of each node, and connectivity is basically telling us each element what nodes is connecting them, is making them. So in this case, the connectivity of element I is N1, N2, N3. Okay. So core is going to be X and Y position of node 1. And then the connectivity will tell me, well, element 1 is connected by node 1, 2, and 3, etc. So we see that core will be a vector containing all the nodes, node 1, node n, and node, the last number is total number of nodes, n and nodes. Whereas the connectivity, sorry, I'll move here. Well, we have for element 1, in this case, connected by nodes 1, 2, and 3. Element I is connected by n1 of element I, n2 of element I, and n3 of element I, just like this one up here. And finally, well, of the last element, E of number of elements is the last value, again will be n1 of E and E. I just forgot to put the subscript here, but this is clear, okay? Now, how do we connect? Okay, sorry, this should appear later, so forget what is here. Sorry for that. So given the element EI and the connectivity N1, N2, and N3 of element EI, okay, we say that each node has 2 global degree of freedom because there's one in X and one in Y. So node 1 will have U1 and U2. Node 2 will have U3, U4. Node N will have U2N and U2N minus 1. Okay, so node 3 will have U2 times 3 is 6 minus 1, 5, and 2 times 3, 6. So U5 and U6. Okay, so let's look at our element I then, and we have node 1, node 2, node 3 of element I, of which we have the local degrees of freedoms 1, 2, 3, 4, 5, 6, which always go from N1, then we go to N2 and N3. Therefore, we can identify the global degree of freedom as U2N1 minus 1, U2N1, U2N2 minus 1, U2N2, U2N3 minus 1, U2N3. So given that, then we can set our connectivity table. Okay, there are many elements. Let's just look at element EI. Okay, and we see that we put the degree of freedom of the element 1, 2, 3, 4, 5, 6, and then of EI, just as we did here. We see that we have U2N of N1 element I minus 1, U2N1 of element I, and there's 1 and 2, 3, 4, 5, 6, just as the figure above. Okay, so we start to see how we're generalizing this, and given this, then we should be able to build the well, at least know where to add the terms of the stiffness matrix of the element EI within the correct position of the global stiffness matrix. So let's try to do it. So here we see the empty global stiffness matrix, and we have element I here. Just reported it. Now, you remember that in the global degree of freedom, what do? Usually we put U1, U2, U3, U4, etc. So we have to put U2N1 of element I minus 1, okay, at a given position, and U2N1 of element I is here, and so on. I didn't put EI as a subscript here, but these are basically filling for element I. The global degree of freedom will be somewhere in this vector, okay? So we're used to fill this matrix, and how do we do it usually? Well, first of all, we associate to each one of these global one. We remember that the local degree of freedom, 1, 2, 3, 4, 5, 6 that we just put there, I just put them here just to remember which one is which. And how do we fill the stiffness matrix? Well, first of all, we remember that, well, if we have rows 2n1e element I minus 1, 2n1 of element I, 2n2 element I, these are the rows and the columns, okay? So where is the position of k 2n1 minus 1, 2n1 minus 1? So we're looking at this, okay? Where is the k corresponding to 2 times this element? So the k, if this was here, the k11, okay? Well, it's in this position. So where will it be? Well, it's going to be in row 2n1 minus 1 and column 2n1 minus 1, okay? Well, if that's the case, where is that? Well, we see it. It's going to be in this position here. You remember? So U1 would have a K11 in position 1, 1. Okay? So we are going to enter a term here. And what term are we going to add? Well, we have a note here on the right. You remember that this global degree of freedom was corresponding to the local 1. So what's going to be here? Exactly. K of the element 1, 1, 1. Okay? Sorry, of element I. Now, another question: where are we going to find k 2n1 2n1? Well, where are we looking at? We're looking at this position, okay? So look at the subscript here, 2n1 2n1. So it's going to be on row 2n1 and column 2n1. And what element stiffness matrix term is going to be in this position? Well, here's our tip, number 2. And therefore we know it's going to be k22 of element I. So if we continue for all the terms and all the combinations, so we can then fill our stiffness matrix with the element stiffness matrix, okay? So let's just give an example without using 2n1e1, too many subscript, and let's just give some numbers to this element I, okay? So let's imagine that our element I was connected by nodes 2, 4, 7. Okay, so we have u 2n minus 1. So 2 times 2, 4 minus 1 is 3. U 2n, 2 times 2 is 4. So u3, u4, and 4 times 2 is 8 minus 1, 7. So u7 and then u8. And 7 times 2 is 14 minus 1, 13. So u13 and u14. So we have our u3, u4, u7, u8, u13, u14. We put them in our vector. And then I ask you, where is K33 going to be positioned? Well, it's going to be positioned in the row 2n1 minus 1, which is 3, and 2n1 minus 1, which is 3. Remember that n1 is 2. So 2 times 2, 4, minus 1, 3. So 3, 3. Well, it's here. Just look at that. And it's 2 times this, so it's going to be row 3, column 3. Where do I cross? Well, there's K1, 1, element I. And then if we look at K44, where is K44 in this position? It's going to be in row 4 and column 4, and we have K22E. Now, where is going, let's do another one. Where is K38 going to be? Well, K38 is, we have 2n1 minus 1, okay, and 2n2. So 3, 8. So row 3, column 8. And we're going to have K, and look at 3, 8. So K is K1, 4. We see it here. And it's going to be in this position. Okay, so we immediately see that the K, the subscript, is telling us where the terms are going. Okay, so we have the row is row 3 and column is column 8. Okay, and then it's U3 and 8. Okay, 3, 8, and then we just look here and then we know that it's 1, 4. Okay, K33 was 3, 3. It's in 3, 3, and it's 2 times 1, so K1, 1, etc. So this is how we do this automatically. And let's try to remember that this is just one element. So what do we, in our example, we had 2 elements, for example. So we have to go through the connectivity array or vector. So it's a, in this case, it's a, we have number of rows is going to be the number of elements, and the number of columns is going to be 3 because we are 3 noded finite elements. So for example, we have the connectivity of our initial problems was 1, 2, 3. This was element 1, 1, 2, 3, and then 4, 3, 2, because this was how we numbered them. So 4, 3, 2, this was our element 2. So let's look at the first element. So we will later we'll see we will loop through all the elements and fill each element stiffness matrix component in the global one. So let's start from element 1 and let's look at node number 1. So node number 1 is associated with what? Well, with U, 2 times 1 is 2 minus 1 is 1. So U1 and U2. And then we have 1, 2 in the local degree of freedom. Then there is node number 2. Well, it's 3, 4 because 2 times 2 minus 1 is 3 and 2 times 2 is 4. So U3 and U4. And node 3, we do 3 times 2 is 6, and then 3 times 2 minus 1 is 5. So U5 and U6. And then once we do that, then we fill the stiffness matrix component in the corresponding position as we just seen in the previous slide. And we add element 1, which I colored in dark orange without putting E1 here because it's going to be too dense. And so we add element 1 stiffness components in the global stiffness matrix like that. Now let's move to element 2, and I will just let me just move myself 1 second. Let me go this side. Okay, so now let's look at element 2. So we have the connectivity of element 2 is connected by node 4, 3, 2. So 4, we do 2n minus 1, u7, and 2n is u8, and then we have 1, 2. So 1, 2. And then we have node 3, we have 2 times 3 is 6 minus 1, 5. So we have u5 and u6. And then 2 times 2 minus 1 is, 2 times 2 minus 1 is 3. So u3, and 2 times 2 is 4, u4. Okay. Now that we have all these terms, we can then set up and fill the matrix. So in position 3, 3, we will have k 5, 5 of element 2. In position 3, 4, row 3, column 4, we will have k of 5, 6. And then position 3, 5, we will have k 5, 3, etc. So we can do that and add them. So if you pause the video and check them out, they should be right. You can look basically, let's look at this one here. This is k 3, 7. So k 3, 7 will have a k 5, 1. K 5, 1. Yeah, I did it right. Okay, perfect. So, and where we don't have anything, we just put zeros. So this is our global stiffness matrix for this problem here. Now, let me just go back to where I was, and let's finish up. So here in this slide, I just put how to automate this in MATLAB. And well, we need x and y vectors to basically tell us the position of the 3 nodes, because we'll need the area to calculate the stiffness matrix of the element, and we need therefore the xy coordinates of the 3 nodes making our element. But this we've seen already. And then we initialize the global stiffness matrix as a matrix of zeros, 2 times the number of nodes, 2 times the number of nodes. And well, the F is the force vector, but we are not going to fill it in this little example. So what happens here? Well, for k that goes from 1 to the element numbers, total number of elements, well, we get the nodes, the element nodes of element k, and then element k plus 1 of all the elements. So for all the elements, we loop and we get the element nodes. And then for I, 1 to 3, we get the x, the coordinates, and the y coordinates of the 3 nodes of the element. We calculate the stiffness matrix of the element. And then we just basically fill the matrix in this way, the global stiffness matrix, using this double for loop. Look at this with patience, and but basically is doing in an automated way what I did in the previous slide. Okay, and here is just to show you, for example, for alpha, well, here it's I, 1, 2, 3, and beta 1, 2, 3. Let's, for alpha equal to 1, then we enter in this loop. For beta is equal to 1, so alpha is 1 and beta is 1. What do? Well, we're filling the stiffness matrix initially is empty in the correct position, so 2n 1 and 2n 1. So these terms here. So if you look at this and zoom in the PDF, you will understand what is happening in each of these lines, and for each position when alpha is 2, and then we enter here, we do for all this, we go and fill up all the terms. Okay, so set this, we're finished in the sense that given the coordinates and the connectivity arrays, or our mesh info, we are now able to, well, using the nodes to identify the global degree of freedoms, the size of the stiffness matrix. And once we know the size, we also understood how to assemble it. So how to fill it using the element stiffness and matrix components. And this was done looping through all the elements and then summing each element stiffness component in the right place inside the global K. So going back to our previous example, I just wanted to show you how this is done in MATLAB using the script of the other slide I've just gone over. And I will use, well, this is our problem. Remember, the solution was 8p over e, and the reaction was minus 2p. Now, if we use lots of ones in the end, our displacement is 8p, so it's going to be 8. U1 is 8 millimeters, U2 is 8 millimeters, and the reaction is minus 2 newtons, okay? This is the core and connectivity matrices or arrays of this particular problem. So let me just start MATLAB, okay, and let's see how this works. So let me just enter MATLAB. Okay, so let me just close all, clear all, and then I choose the type of problem. We will stay in plane stress. This will affect basically our element stiffness matrix. And so this is exactly as we had last week, okay? Now, let's run it and pause here for a second. So if we have, we do a step, we see the element number. We have 2 elements, okay? Perfect. Then the node number we have, I just do the size of coordinate and I get the number 1. So I get the number of rows. And the number of rows is 4, okay? So these are the node numbers. And then, well, computing the stiffness matrix, I just show it over here. And I initialize our arrays just for saving time, because once in computer, and I mean, if you initialize the size of an object and then fill it, is much more efficient than working and looping through something that continuously grows, okay? In this way, the computer already knows the size of our arrays and matrices, and it will be much faster. And so now we loop for all the elements, okay? We get n is the connectivity of element, well, now k is 1 of element 1, was joined in fact by node 1, 2, and 3. Now, node 1, 2, and 3, we have x and y. Well, they were at the origin, so x was the coordinate of, well, now I is 1, so we're looking at node 1. Node 1 is in position 0. Now we have to finish the loop. Node 2 will have an x of 1 and a y of 0. And then node 3 will have an x of 0 and y of 0, okay? Sorry, y of 2. So now x is 0, 1, 0 and y is 0, 0, 2. So the positions of x of node 1 is 0, of node 2 is 1, and node 3 is 0. The position y of node 1 is 0, the position of y of node 2 is 0, the position of node 3 is 2. So given these, we can then calculate the element stiffness matrix of element 1. So we enter this function, we've seen this already, but this returns the element stiffness matrix. And now we basically position the element stiffness components in the right position in the global stiffness matrix, as we've seen in the example. I will not do all the 4s, otherwise I will never end, but basically we do it for element 1. Now we see that the global stiffness matrix, oh sorry, I have to, this is for I is equal to 1. We've filled these terms, okay? And for I equals to 1, basically we're doing U1 and U2, because node 1, okay, had U1 and U2. Now, when I is equal to 3, we will see that we'll fill the next 2 rows, etc. In fact, we do a continue, I go back, I've done a loop, and in fact, I've filled U3 and U4. Then I continue, and now I is now equal to 3, and I've filled U5 and U6, okay? This was for element 1. Now, if I step, then I get element 2. You see that now element 2. And then if I continue, I basically get the x and y coordinates of the nodes 1, 2, and 3, well, making the element of element 2, so of node 4, 3, 2, and then again we loop and we fill the stiffness matrix, okay, for element 2. So I've done that 1, 2, and 3. Now the element stiffness matrix, we see that if we step, then we go out. Now this is the global stiffness matrix assembled as I've done manually before. You remembered we had 4 zeros in the top and bottom, right and left respectively corners, and this is the penalty method. So we have 5, 6 constraints. So basically this is saying that I have a constraint in the y direction on of node 1, and then this is in the y direction of node 2, in the y, I think this is the x direction of node, well, these are all the constraints, so you can look at them with more patience in the MATLAB. So we build our V stiffness constraint array. This is the penalty method, so I will not stop too much, but over here we calculate our penalized stiffness matrix. So our solution is now calculated, and we see that if I continue, U1, they will appear here. So let me just give some more space. And so U1 is 8 millimeters. Oh, this looks like familiar. This is correct. U3, oh, 8 millimeters. Whereas the ones that are basically 0 and numerical 0 are 0 because there was a constraint there. So this is our solution. Let's see if our reaction is correct. And then, well, here we get all the reactions. And where there was no reaction, well, basically you see that there is no value. So there is no force, practically a 0. So set this, let's see if we can plot our deformed mesh. Well, here we calculate the position of the deformed mesh by adding the nodal coordinates of our initial node plus the displacement of the solution in x and y respectively. And then I plot my function, which should appear here. I'm not displaying it because it's hidden there. Okay, where is it? Here it is. Okay, so yes, this was our element that is deformed because of the pressure applied here on the left and the load on this node here on the right. So set this, I have concluded. No. So thank you for listening. I hope this was clear. You now have a tool that can be used to check the solution of your coursework. So if you've reached to the end of this video, this is perhaps a nice tip for you. Use the MATLAB and check the solution, just putting some values and see if what you solved by hand is correct.